mic. Okay, so these two speakers are here. They are present. And I don't know what to say about them except that I am one of them. And Jonan is the other one of them.
Do I need to get turned on? Can you guys hear me? Oh, I am mic'd up. Okay. I'm the other one of the two Rubyists changing the world. It's a very exciting time.
Okay, so we practiced this last night, but we did not have a clicker.
The clicker is going to change everything. You
yes.
guys are going to be amazed. So much better with a clicker.
All right, so we are here today to talk to you about the future of computer vision. Actually, let me set this up here so we can see what's ahead, so that we can cheat. And you can't.
You guys have no idea what's about to happen, but we can see it right there. It's amazing. It's the future. We're seeing into the future with computers.
With computer vision. Okay, all right, so let's get started. All right, so we're going to talk about the future of computer vision with us and how we are changing the entire world.
And first, it's about me. I'm Jonan. I am LeapBot on Twitter. I work at New Relic up in Portland. Hi, New Relic, up in Portland. If you're looking for work, we are hiring. It's a great company. And if you want help installing New Relic, I'm happy to be there for you.
Do you want to?
I want to click.
You click.
So I actually, I now write software. And when I was a kid, I wanted to be a spaceman instead of that. This is a gift from one of the organizers here, Josh Sullivan. He made this for me when I worked at G5. Instead, I have to pass my time building Lego robots and scanning magic cards. It's really pretty terrible, actually. But if there are any spaceman recruiters here, hit me up after this.
And I am Aaron Patterson. You may know me from such things as emceeing this conference. Thank you all of you for having this magical gathering today. That is me and my cat. Let's do this. We only have 30 minutes and a lot of stuff to show you. So, yes, we're here today to talk to you about Magic the Gathering. This is a magical gathering.
Who's played Magic? Has anybody played Magic the Gathering? A lot of nerds
Sweet.
in the house?
Okay,
Sweet.
Yes.
You're going to fit right in here. Magic the Gathering is a collectible card game, for those who don't know. So you buy little packs of 15 cards for too much money, and then you hoard them in your garage.
So you get totally addicted to the game, and I am totally addicted. If you followed my Twitter, I spent my lunch money on buying these stupid cards yesterday instead of eating. So I basically started playing this game, like, I think 20 years ago in high school. And then I quit for a while, and then I started playing it. Like, of course, when you're in high school, you don't have, $1 million to spend on these stupid things, so I quit. And then, 10 years ago, I started playing again when I had a real job and spent way too much money on it.
Way too much.
And then I quit, and now, like, somebody got me addicted again.
I don't know anything about that, but I have a similar story, actually. I've been playing for about the same amount of time, except that I just never stopped instead of stopping, which is a way better way to do it.
So basically, I have too many cards. Like, I opened up my closet. I have about 6,000, probably over 6,000 cards in my closet. I just started playing again. I have no idea what they do. I decided to go play with a friend, and then I just got destroyed, and it sucked. I was sad. So I have no idea what all my cards do, and I want to know that. And I also want to know, are they worth any money? Because maybe I should just sell these stupid things that have ruined so much of my life. And I also have many more other problems.
Many more.
I have many other problems besides that, but those are some of them.
My problems. It's cute that Aaron says he has too many cards. He has about 6,000 cards. I think I have 100,000-ish, give or take 20,000. I'm not positive. It takes up a lot of my garage. I'd like to count those, so I know for sure. Hard work is hard. I am an old man, and hunching over my coffee table sorting cards is not my idea of a good time. And valuing collections quickly is difficult. This is a thing that I do as a hobby. I buy a collection on Craigslist, and I keep the bits I want, and I sell the bits I don't want, and I make my money back and go again. If anyone's selling their Magic cards, hit me up. Okay, and I want to stop buying cards that I already have. I'm really tired of finding cards later that I've purchased at the store that night for my deck, because I couldn't sort through 100,000 cards fast enough.
So we needed to solve these problems, and we're both super lazy. It sounds like the perfect job for a computer. Computers are built as our slaves. They do repetitive tasks for us. This seems like a super repetitive task. So today we're going to talk to you about our solutions for dealing with these particular problems. I don't remember what slide is next.
It's this one.
Next one. Yeah, so we're going to talk about robotics, artificial intelligence, AI, cats. That one's important. And then like cameras and stuff. We're going to talk about let's do next slide.
We want to give you this first.
We're going to talk about, like, this is a roadmap of our talk today. We're going to go over the high-level solution. Like, basically, from a high level, we both implemented the same thing. But unfortunately, they're different. And we're going to go over the specific implementations.
They're different here. See the red and the green? That's where it forked.
Yes.
You know, like you can't do on Windows? That's us right there.
Yep. So we're going to discuss like our particular solutions to this problem, and then maybe we'll talk about future work and maybe why we couldn't work together. Mainly it's because I hate Jonan.
It's
he beats
true.
me
We
at
have a
Magic
really hard
all the
time getting along. It's my elf deck. It keeps beating him.
So from a high level, basically both of our systems do this. They take a photo. So they just take a photo of the magic card, and then they try to extract a card from that photo. So like we have some card, like there's a card in the photo. We need to pull the card out of the photo. Then we need to identify the card. So the system tries to identify what card it took a picture of, and then it saves off that data because we need to keep an inventory of the cards that we have.
We want to know what we have. He wants to figure out different cards that he has with their ratings. I want to count my whole collection. So we save the data at the end.
So then we just basically repeat this process over and over and over again.
Or rather, robots do, and we don't.
Yes, that is the plan anyway. So basically, we kind of glossed over that particular card identification section.
That's the easy part. Don't worry about this part.
So we're going to talk about exactly how the card identification system works. We start out with a corpus of data. This is like we have some knowledge about the cards, and the way that we acquired this knowledge is we got a bunch of images.
Online, we have a bunch of images. Just in general, to solve this problem, you could have a corpus of data, something known, right? This is the solution to the problem already. We start with a bit of solution, right?
So we have a bunch of images, and we know these images are tied to particular data.
Exactly.
So
this image is a picture of this card, and we know that if those images match the images we take, we're close, right?
So what our systems do is the first thing is they take that corpus and they try to match the image against what we have in the corpus of data, and it makes a guess. So the system will guess at what the card is.
And it'll prompt us. It'll say, I think this thing is a forest. And I'll say, you're a bad robot. It's an island. You're terrible at everything, and you should feel terrible.
So it prompts us saying, like, hey, is this the right card? I made a guess. I'm not sure. Can you tell me? So the next thing we do is we teach the system whether or not it was right. So
I was unnecessarily mean to my robot right now. Urza's a good robot. I do teach Urza to be better.
So we say, like, yes, you got it right, or no, you got it wrong. And once we do that, then we save off that data. Like, we tell it the right answer, and then our corpus gets larger. So it learns from this. We say, like, okay, good job, you did it, or no, this is the correct answer. And then we basically repeat this process, and I think we can fast forward to the next slides.
Enhance.
Yes.
More. And learning. Look at that. That's learning. That's
so
what
we
it looks
basically
like.
repeat this process, and every time we repeat the process, the system gets smarter. So we
smart.
can say that this is artificial intelligence.
Truly artificial. Urza's a dumb robot.
Every time the corpus gets larger, it gets better at guessing what those scanned cards are.
Right. It's a learning system. The data model. We're going to talk a little bit about how we have to model the data because it's actually kind of an interesting problem when it comes to magic cards. You would think one little card, one little image. We'll get into that in a second here. But here are the cards.
So we store cards. We have a card model, and we store a bunch of cards in our system, and we have to store information about the cards, particularly the name, the image. We have to store the expansion set, and this is important because a card can be reprinted between expansions, and the value changes drastically between the expansions. And then also, since I suck super hard at Magic, I want to know what the rating is, so I store off the rating for those, so I can say, like, hey, tell me what the best cards are in my system.
This is our make Aaron a better Magic player data set here on the bottom, the stars.
So we think, like, okay, that's great. Well, we store an image. So we have a card, and the card has one image, and that's great. So
Seems reasonable, right, Magic players?
Right? Are we cool with that?
Sounds legit. Anybody ever seen this card? That's one card, and it has two images. And it's called Big Furry Monster, and they printed it to troll programmers who try to scrape their site later. So we think, okay, great. Now we have a new model, right? All right, an image belongs to a card, and the card has
many images. Are we good with that?
Sounds good? David thinks so. He's a Magic player. He would know.
He is wrong.
Yeah, not so much. Here's an image with 2 cards. Good job, Wizards. Thank you so much for your help. They made these cute little half cards, and you could turn them sideways and cut them in half and use them as tokens. They were adorable and terrible to model. So we end up with this. Image has and belongs to many cards. Card has and belongs to many images.
So our overall data model looks like this, and we're going to talk about hashes here in a second. But basically, we have cards. Cards have and belong to many images, and then cards also have many hashes, and we're going to talk about exactly what the hashes are next.
Hashes are very exciting. That's the recognition piece of this talk we want to get back into. That easy part that we kind of glossed over earlier, we're just going to spend the rest of the time talking about that. Recognition is actually a pretty hard problem. We use what's called a perceptual hash. Has anybody here ever done OCR? Did you look at this problem and say, like, oh, you just OCR the cards? No, because you're smarter than that. You've tried to do this. It's ridiculously hard, right? Like, OCR is almost always wrong and very difficult to work with. So we didn't do that. We used perceptual hashes, which is basically like a hash of the image that if the human eye thinks the 2 images look similar, the hashes that come out of this perceptual hash will also be similar. That's the theory behind all of this.
Think about it as it's exactly the same as producing a hash key for some object. We're just producing a hash for an image, right? So let's take a look at what that looks like. On the left here, we have a reference card. This is a card from our corpus, one that is known. On the right side, we have one that is unknown, something that I was able to pull off of an image. And at the bottom, you can see we have 2 numbers, and those are actually the hashes. So the left side is our known good hash, the right side is some hash, and we need to know how close they are together.
This is our corpus here, right, on the left. So we use the Hamming distance to calculate that. We compare those 2 strings for differentiness, effectively, and the Hamming distance is the number of transformations you have to make on one to make it exactly the other, right, number by number.
So what that means is that the lower the Hamming distance, the closer the images are together. So if we take a look at this one, we'll see, like, okay, we got a number here, and then if we look at the Hamming distance for that, it's 28. So clearly that first image was much closer than this one. So
very different. A brief disclaimer here, it is possible for very distinct images to have similar p-hashes. And sometimes it comes up, so our system needs to prepare for that.
So anyway, we save these hash keys off, and so adding these hashes to our system increases the knowledge in the system.
Remember when we embiggened the learning? That was this right here. We store the keys again. So next time, we're better. Urza gets smarter over time. So we're going to talk a little bit about divergent work here, where our solutions went their own separate paths. We have similar things for data, and we have similar things for hashing. But this is where we diverge. So I built a fixed environment solution that you see before you here out of Legos. This is Urza the robot. And I'm going to talk a little bit about designing Urza real quick. So I need a way to dispense cards, and it's very important to me that I dispense those cards safely. It's a difficult thing to dispense cards without damaging them, because Magic cards have a very fragile varnish on the top. So obviously I want to take good care of my cards. I want to scan the cards. I want to know what I have, and then I want to be able to sort them. This whole tower actually rotates around, and I can sort into distinct piles by any arbitrary criteria on a Magic card. So those are the 3 things that I wanted out of my system. And I chose to build it using Lego Next bricks. Has anybody ever used the Lego Next brick? They're pretty cool. There's a little GUI tool you can use to program them. The GUI tool is not ideal in this case. It's good for like making robots that chase colored balls. But in this case, I wanted to use this gem called Lego Next. It's written by a very smart man named Christian Doc Watt on GitHub. You should check out this gem. I wrote the piano example, the one that doesn't work totally. It's awesome. You should play. Anyway, Lego Next communicates with the brick over USB or Bluetooth, and it allows me to send commands like, hey, run the motor, or check the light sensor and see if the light changed, right? Makes it very easy to work with. So the dispenser here on the top, I have a light sensor on the tip, light sensor. It's a small little bit here. Looks like this, and it actually can detect color, but I'm not using that functionality of this. It just tells me whether or not the light has changed. If it was dark and it got lighter by 7, which is arbitrary value I get back from the light sensor, then I know that something changed, or lighter, right? Lighter or darker. So I need this light sensor so that I can run the first motor until a card comes out.
So the idea is that we run the motor, and then we know when to stop the motor because the light sensor changed. So it just feeds a card over until it covers the light sensor, and then we know, hey, it's time to stop the motor.
The alternative being to just like run the motor for 0.7 seconds, but obviously that gets out of sync after a while. So then we have the camera. The camera, I really wanted a variable distance and variable focal length.
The camera is here.
Camera's here. It's the one with the duct tape on it. That last part, variable focal length, turns out to be hard on Macs. There are very few webcams that actually do that. Microsoft LifeCam, the one Aaron bought, it happens to be one, but you can't focus with my camera because it's from Logitech. So That's a Mac feature. The driver that they have, there's a universal webcam driver, which means universally not going to work with Logitech.
So in order to change the focal length,
in order to change the focal length, I bought some glasses at the dollar store, and I ripped the lenses out of them, and I duct taped them to the tip of the camera, which you're welcome to see later. I spent $5 buying 5 different. So it is a questionably variable focal length. I could change it, hypothetically. And this is what I get. This is the fixed environment advantage. I know that my card's going to drop vertically into my screen and be perfectly in the middle, and I just have to set my cropping distances, take 489 pixels off the top, and I will end up with something close to this on the right, which is the reference image.
So he's able to mount the camera at a 90-degree angle to the card.
Exactly.
And also know every time this feeds where the card's going to land. So all he has to do is say, like, okay, I'm going to crop off some number of pixels.
Off the sides of the card, and then I'll end up with something close to the reference image. So for the software inside of this, aside from the Lego Next gem, I'm using 3 other gems. I'm using RMagic to handle the cropping. Pretty easy to do. I'm using Fashion, a gem by Mike Perham. It's maintained by somebody else now, but the Fashion handles the fingerprints, the hashes that we're going to show you a little bit more about here in a second. And then AV Capture. It turns out that all of the gems for handling webcams on Macs were not super, so we had Aaron write a thing.
Yeah, so I wrote one.
Yeah. Mining data. This is where things diverge for me a little bit. So I want to talk actually briefly, real quick here. I was mining data with a gem that I wrote called Gatherer the Magicking. And it was a really long process. It took me several months, actually, to write the gem, and it still wouldn't work. Sometimes things move around on the page. The actual site where I'm scraping from is called Gatherer. It's the official Wizards database of all of the cards and all of the data. It was where we got those pictures earlier we showed you. So I was trying to scrape that site to get my own database and be responsible for keeping it up to date and all of that. And I finally figured out the secret to making my stuff less brittle, and I was about to finish my gem, and this jerk that I know IM'd me. His name's Mark Turner, and he sent me a link to this website, and he's like, yo, bro, you just wasted your whole life. You should stop. And so I got this MTG JSON site, and it's just, any kind of API I could possibly want and all the data in JSON format. So that's pretty nice. We use that now instead. And
He uses that now instead.
I use that,
We'll get to that.
Yeah, I use that now, yeah. So MTG images here, there's an API to access the images as well. So these multiverse IDs, these uniquely identify Magic cards within the system. Even Big Furry Monster has a multiverse ID. Happens to have 2 images. Screw you, Wizards. Recognizing cards. So I have 3 different methods that I use to recognize cards. This is the obvious one right here, is if I have a Hamming distance that is less than or equal to 6, I say we're good, right? It's not that simple, really. Like, I will have false positives, but I have fewer false positives doing this than I would with a higher number. I tuned this with science and trial and error in several hours of my time. 6 is the correct number. The second method that I have for identifying cards is searching for duplicate fingerprints. So I have this method that returns to me all of the Hamming distances of all of the cards, kind of like a hash type structure where a Hamming distance of 10 points to this array of cards, and cards can be duplicated in there. I just keep putting them in. So if I have 7 fingerprints for a card, and it happens to have a 10, a 12, and a 14 for those various fingerprints, then when I look at the lowest 3 Hamming distance groups of cards, I'll see that one card appears in there 7 times, and nothing else is duplicated in there. So it's very likely that that's the correct card. So I'll choose that card. If I see it 5 times, I assume it's the correct card. If I see it 7 times, the machine actually learns from itself. And it says, okay, well, I trust that this 7 duplicate is the actual card, and I'll save the next fingerprint. So the next time we come through, we'll see 8. And finally, there's the guess and prompt, right? The part where I push a yes with my finger. And that's the last step for Urza. And then when I train Urza, hopefully next time it will learn and not bother me anymore. So advantages of this system. There are advantages to Urza? I can't remember what
the advantages are that your code is actually very simple.
Oh, right. Yes, that's true.
You know where the card is at any point.
Yeah.
The other advantage is that you don't need to do anything. The machine just feeds the cards through.
Just feeds it out. I can let Urza do this while I watch TV or play Magic with Aaron, and Urza can just scan my collection for me, ideally. And then there are some pretty serious disadvantages. That being that every time I move Urza, because I wanted that variable camera length, I have to recalibrate the camera and the pixel distances and all of that. In fact, just carrying the table out here may have miscalibrated the camera. We'll see later at the end here. But the disadvantages of this system are that it's pretty fragile, really.
Though that's solvable
That is solvable.
Yes.
Absolutely. As this is just a prototype, right? If I were to build this as a static machine, like maybe an acrylic box with a camera on top, it wouldn't have that problem. And there's another disadvantage, and that is the expense. Lego Next, this system here, is actually pretty expensive. It's like $300 for one of these kits. You can find them cheaper on Craigslist, maybe less than $100. I got mine for $75. I just recently traded 2 Raspberry Pis for another one. Thank you, Adam. But I think this is a pretty big disadvantage, but it's really nice for prototyping this kind of thing. So we're going to talk about freestyle.
I will take the clicker now.
For you, sir.
Thank you. So this is my far inferior solution to the same problem, and I'm going to talk about that. So I like to call mine the freestyle environment.
For freedom.
One, because it sounds cool, and 2, actually that's the only reason. So what mine looks like is this. So basically what I have here on the right is I've got a light box hooked up to a webcam, and that webcam is hooked into my computer, and then there's this freaking cat that's always messing with my stuff. And so it's basically I got this camera that's pointing right into my light box, and if you look from the camera's perspective, you'll see the camera points right in there at the card and gets a picture of the card. Problem with this is that you can see compared to his, it's not mounted at a 90-degree angle, which kind of sucks because the card is it's not rectangular anymore when you take a photo of it. The other problem is that this card can be anywhere inside the image. What was really nice about his is it was okay, it's right here, we can crop it. Mine, I have to actually find the stupid thing, crop it out of the image, and then somehow resize it so that it's rectangular, and we're going to talk about how I do that. So the software I use for that is OpenCV, and I'm going to talk a little bit about mining data. I wrote a thing that scrapes all of the Magic the Gathering website and puts all of the stuff in my database, so I wasted my entire life. I hate you, Mark Turner. I did not know about this awesome website with the JSON, so I wasted my life. Anyway, that's what happens in my system. Once I get that data, I use OpenCV. OpenCV is what actually extracts the card from the image, and I'm going to talk about how to use OpenCV to do that. So the issue is I'm going to show you what we have, and then I'm going to show you what we want. What we have is an image that looks like this. It's totally washed out here, but that's fine. You can see it's just a card that's inside some image. And the problem is, it's not rectangular, and it can be anywhere in here because I'm doing this with my hand. It just goes in there. And I guess that's
But if you compare this to a reference image, it's going to be crazy bad, right?
Yes.
It might be better than a red card, but you're still not going to know any real information about what you have.
So what we want is we want to have something that looks like this. This is what it needs to look like so that we can compare it against the original. So we need something that's rectangular, and we need something that's, we need it to be rectangular, and we need it to be, I don't know, cropped, basically. So the way that we do card extraction with OpenCV, we do it in only 8 easy steps.
Only 8 easy steps. It's so easy. Call now, folks.
It's really, really easy.
1-800-CARDBOT. Buy.
I'm going to show you exactly how easy it is. So we start out with a card like this. This is our starting image. We pre-process it, turn it to grayscale with OpenCV. So once we have a grayscaled image like this, then we can feed it into an algorithm for doing edge detection. So OpenCV gives us an algorithm called the Canny edge detector. I have no idea how it works. You should go read the Wikipedia page. But it finds all of the edges it finds all the edges in the image.
Like this. Do we have a slide?
So you just feed it in and say hey, tell me the edges, and we get an image back that represents all the edges in the image. This is what it looks like.
It's uncanny, right?
All the white stuff, all those white lines are the edges in the image, and unfortunately, they are not the edges that we want.
None of those.
Not all of them are. We only want that one around the outside of the card, so we have to figure out which one that is. The way we do that is we say hey, OpenCV, tell me all the contours in here. And what contours are just edges, shapes in the image. And we need to say okay, I don't want any contours that are holes. So tell me all the contours in here that are not holes. So that's what this does, is filter out any holes. You may be asking yourself, what the heck is a hole? Well, around the edge of the card, we have a contour. And on the inside of it, we have a hole. So a hole is something that's literally cutting a hole inside of your outer contour. So we only want these bounding ones, these outside ones, and we want to eliminate the holes. We don't care about those. We want to get that one around the outside. So we filter all those out, and if you draw all the contours that we have available, this is what it looks like. looks exactly the same as the edge detection stuff. So then we say, like, I just want the largest contour, because that's what we want in this image. So we say, sort all of those by the contour area. Then we end up with this. So now we actually have a shape that represents the contour of the card, but we need to get a polygon out of it. So we say, hey, OpenCV, give me a polygon for this, a polygon that represents the shape. And then we try to get a convex hull for that. Everybody remembers Davy's talk
If you
from
have questions
yesterday,
about that,
right?
ask Davy. Yeah,
Woo!
Davy knows it.
No idea how it works. It's all magic.
Davy's got the convex holes.
This code is magic to me. Anyway, so we get a convex hull, and then how much time do we have?
We have 10 minutes. We're good.
Well, I want to go over it. So one thing that's super duper annoying about OpenCV is that the documentation kind of sucks. And so I had to go read the code for it in order to figure out what it does. So I'm actually sifting through this C++ library. And I'm like, I need to get a bunch of points, the convex hull for this. And supposedly the points for this convex hull are returned to you in clockwise order. So if you look at it, you give it this constant that's like, okay, put it in clockwise order. And so I did that, and it turns out that if you specify clockwise, it actually gives it to you counterclockwise.
Where clockwise means counterclockwise.
And
obviously.
so I was like, I hate you. Which is why I've got that reverse right there.
Just flip it.
Like, okay, no, I actually want it in clockwise order. Anyway, so we find the polygon, get the convex hull, get the clockwise points, and if we plot that, we'll see, like, okay, we actually got 4 points. That's where they are at the edge of the card, so we can actually extract the card from this image. The way we do that is we have to get a warp matrix. So we say, like, we have to have a matrix that knows how to warp the image so that we get back a rectangular card. So we say, okay, I want a card that's 230 pixels wide and 300 pixels tall. Give me a matrix that can transform this image such that that happens. So we ask OpenCV, give us back a matrix for that. It's really exciting. Then we have this warp thing happening here. Our warp matrix. So we feed the warp matrix back into OpenCV, say like, hey, transform this image now. And once we transform the image, you'll see that it looks like this. So the image looks all messed up, but it actually warps the image such that our card is now rectangular rather than trapezoidal, and it's in the upper left-hand corner.
At a known width and height. That's important here.
Yes, we know the width and height in the upper left-hand corner. So of course, like, this is really exciting. We need to get our return on investment here, so we set the return on investment.
We're trying to make money here. We got to sell the cards.
So
that's
we
our priority.
Sell this.
Yeah.
So we say, OpenCV, give me the return on investment. I'm just kidding. What ROI stands for is region of interest. So we say, like, I'm interested in the upper left-hand corner there, and it slices that out, and we actually get the card now.
Throw away the rest.
It's just that easy.
8 steps. Call now, folks.
Yes, small amount, tiny amount of work to do this.
1-800-MAGIC-BOT.
Also, by the way, so the OpenCV documentation is super terrible, so I was like, you know what, I'm going to buy a book. Buy a book on OpenCV. So I go to the O'Reilly website, I'm like, oh, there's a book here. Let's look at that. And I'm like, oh, this looks great. It's a new book. And I look at the authors, and I'm like, oh, that's interesting. And then I go back and look at the OpenCV website. I'm like, I wonder who wrote OpenCV. Well, the authors of this book are the same people who wrote OpenCV. And I was like, I hate you. Why didn't you just write the documentation? Now I got to buy this book. Anyway, so I bought the book. It's just that easy, folks. Just that easy. So here it is. I'm going to show you my system in action, like a video of my system actually working. So over there is the live feed from the camera. So I put a card in here, and you see it scanning. That card on the left there is the image that it recognized from the video. That one on the next to it is what the system thinks it is. So I click on the one that I want, and then it saves it to the database. And as soon as it saves it to the database, you see we end up with 2 stone rains there because it's learning from that.
Is this by Hamming distance, right? Like
yes.
The closest by Hamming distance.
So this is ordered by Hamming distance along the top there.
Incidentally, if you have ever played a stone rain, you're a terrible person, and I will never play Magic with you.
So that's actually how this system works. I can answer the questions now with the system. I can say, what do I have? So I can do this query and know what cards I have, and then I can say, like, how good are they? And now I can become a better Magic player from knowing this. And in fact, I'll show you the best card in my collection. This is the best card in my collection. It's pretty good.
It's a pretty good card.
I like this card. And then I'm going to show you the worst card in my collection, which was this.
This card is terrible.
This card is super duper terrible.
I want to explain just real quick for non-Magic players. This card costs 5, and it's a resource-limited game. You get 1 more every turn of the game. So on the 5th turn, you can cast this card. And what it does is it gives a creature haste. It lets it attack the first turn. You also have to cast that creature on the same turn. Otherwise, it'd be able to attack anyway. So it's 5+. We're looking at like turn 10. By turn 10, if you're trying to give a creature haste and attack your opponent, you're already dead. This is a really bad card.
So, of course, I had to go click on the forum for this and read the comments. It's pretty hilarious. Anyway, this is the worst card in my system. So the advantages of my system are that it's very cheap. So you have to build this light box, which I didn't even do. My wife did that, so boom, free labor. The only other thing that you need is you need to have the webcam. The webcam cost me like 30 or 40 bucks. So all that's really involved in my system is a wife.
Thank you, Abby.
Yes, thank you, Abby, if you're watching. A light box and a camera. So that's all you need for this. And the disadvantages are numerous. You actually have to feed the card in there and then like recognize the card, and you don't know where it is. So the disadvantages are complexity of code. It's also like it's a manual process. I have to feed that card in there, unless maybe I could talk my wife into doing that, which I doubt.
Good luck. He's his own dispenser. He's just got to throw him in and pull him out. Train the cat. If Gorby could do this work, I think.
No, he just sleeps on the stupid box. It's warm because I got the light there. And he's like, oh. So that's the other problem with the system. Actually, another advantage is like I don't have this calibration issue. It mostly just works. Oh, another huge disadvantage is that sometimes OpenCV doesn't find the image or doesn't find a card in the image. So I actually have to feed video to OpenCV. So this is actually video going through the system, and I didn't think that was that bad. And we've
got it. We got it. I've been assured that we're all right.
All right. So future work, stuff we want to do together in the future. We want to graduate our machines so that they can learn on their own.
I'm going to get Urza a little cap and gown and go off into the big bad world. So I would like for Urza the corpus to reach a point that we don't have to train it manually anymore, right? My job mostly is to watch it scan one card, and it will say, is this an island? And I will say, you're wrong. You're a bad robot, right? And then it learns over time. I can filter the card names as I go through. I may be able to show you guys that. But the idea is that we build the corpus up to a certain size, and with machine learning, nothing is ever 100% accurate, really. So I could get it up to 99%, and then after that, it will still have questions. But I don't necessarily have to use my fingers to answer those questions,
so
it turns out.
Yeah, hopefully we can farm off answering those questions, say to Mechanical
Turk. Human fingers are for sale on the internet. You can hire people to do that work. Click the thing. Just show them the image, or several of them the image, because some of them lie and some of them steal. I'm lazy.
So the other thing I want to do is I want this thing to build a deck for me so that I can just have the system build a deck. So next time I go play at a Magic tournament and I'm playing against some 13-year-old kid, I won't have my mother insulted all the time.
It's like Call of Duty in real life,
yes.
And they can slap you too. They're right there. They can actually hit you.
That's exactly what it's like if you go to one of these things. It's a war zone. The other thing we want to do is having pricing and commercial purposes. I mean, selling this system, which hopefully we will demo here shortly.
Yes, we will demo the system, but ideally it will be smaller and less fragile than this, and you could make a thing that people would buy, I imagine. Somebody sold like an iPad button pusher on Tindy for $100,000 worth of orders. I could probably sell this, I think.
At least 100,000.
Yes. We're taking VC if anyone's interested. I'm quitting my job today. I'm just kidding, Sam. Please don't fire me. And
we're looking at least 1 or 2 Instagrams here. Okay?
I think so. I'm thinking,
at least 1 or 2.
If you've got a couple Instagrams to spend, hit us up.
So, all right. So we'll talk shortly about why we couldn't merge and then hopefully demo this. So Jonan and I, we were talking about this, having our systems, and we're like, you know what, we're going to get together and merge these two together, and it will be amazing. Amazing. So he came up to Seattle, and we started working on it together, and we were like, okay, we're getting the code, working together, and then I realized we couldn't do it. The reason we couldn't do it is, the first reason is installing OpenCV is hard. So we're like, well, you know what? I don't want to install OpenCV on Jonan's laptop. Let's do this instead. We'll have Jonan's laptop take a photo, This is the obvious solution to this problem. We'll have him take a photo,
It's brilliant.
send it over the network to my machine. My machine will cut out the image and get the hash.
Wire up a DRB process. It's
Yes,
easy.
we'll have DRB,
Yep.
of course, because it's Ruby. We'll DRB it over, and then I'll DRB it back, and then he'll be able to identify this, and it's really awesome because then we'll have a distributed magic card identification system.
An
which then-
artificially intelligent distributed magic card identification system.
It means we can put it in the cloud.
The cloud is, I think, essential part of this.
That would add at least 2 or 3 Instagrams.
That's true, just there, yeah.
But it turns out that since OpenCV cannot, OpenCV requires video, that means we would have to be streaming video over the network.
It's like Netflix and MagicBot put together. It's easy.
So this sounded a bit too hard, so we did not merge it. Fixed cropping is much easier. And I think, like, can you demo this now?
I've been told that I can. Urza lies all the time. This is Urza. Urza's a terrible robot. I need to be able to plug this in, actually. That was poor planning on my part. I wonder if we can make that happen. Probably not.
Why do you have to plug it in?
I was going to try and show what was on the screen, but I'm not going to anymore. I just changed my mind.
Turn the laptop around.
I will turn the laptop around this way.
Everybody squint.
Everybody squint really tiny. Oh, we got an extension cord. Look at this. Blomage is one of my favorite Rubyists today.
Why wouldn't I travel with an extension cord?
That's just what we do. I know, right? So Urza is a little bit fragile. Like I said, you've got this light sensor, and the light sensor has to detect a light change of plus or minus 7, and it has to detect that in varied light conditions. And I have this light box that is not a light box, so the light that comes across the card can change from picture to picture. Right? This is one of the advantages of Aaron's system that we didn't really get to touch on, but my entire setup here depends very much on the environment where the robot exists. So it is possible that this will just explode. Like, robot may kill us all, all right? Just be prepared for that. You in the back, run for your lives. Tell my children I love them. This is way less dangerous than my presentation last year.
His password is dots. Know your password.
Dun, 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 dun. Okay. I have that over here, and I have this over here. And I built this as a Rails engine because I intend to build a site out of it here in a little bit. And I need to turn off the logging because, oh my gosh, I load up all the cards into memory as I create my first bot here. So I create a new Urza bot. Oops. There's my first one.
Fails.
And it fails. Hey!
Woo, thank you. That was it.
So the Lego brick, I have the Lego brick hooked up via USB, and I have to be able to communicate with the Lego brick. And it periodically goes to sleep. Like if you were to talk for 40 minutes and then try and use it, it'll be asleep by then. So I think if I do this now, I'll get back nothing. And I can say, hey, robot.
I'm so nervous.
I know. Please just do a thing. Don't kill us. It dispenses one card. It takes a picture of it. Slowly, but surely, and it pops it up here in the preview window. It's Phantom General. What do you think it is? Is it Arcane Laboratory? No.
No.
That's not even really close. That's a blue card from a different set with different art. But I can filter it. So this is, I can type in here now, Phantom. Is it Phantom General? Yeah, it found it pretty quickly, so I can tell the hamming distances were close on those cards. And now I'm saving the fingerprint, and the fingerprint is saved in there. And I'm feeling confident, so you know what? Let's just do this here. Just keep learning, robot. What could possibly go wrong? It'll dispense another couple cards there. There we go. Trestle Troll. Nope, not Child of Night. Let's filter it, and we'll say this is a Trestle. Is it Trestle Troll? Yep, saves the fingerprint. Next time it sees that, it should be more likely to recognize it. This one here, it says, using common fingerprint, Rakdos Ragemut. That was that thing that I discussed earlier.
So it automatically identified that card.
And it automatically identified this card, Nivix Guildmage. And this one, Common Bond. And it will just keep going through these until it explodes. Survey the wreckage. Thank you very much. It actually did a thing.
So the awesome thing about being the MC and a speaker is that we can run as long as we want.
We're just going to keep talking.
Actually, I think we're probably out of time.
We are out of time, and we are done. Please, if you have questions about the robot or recommendations about how you can recognize perceptual hashes more efficiently, and or VC.
Yep. 3 Instagrams, 4 Instagrams.
3 or 4.
We'll take 5.
Yeah. Thank you very much.
Thank you.